Hello, everyone, and welcome to week 8 in database systems. Jumping right into our agenda, first we'll go over the assignments, and then we'll talk a little bit about chapter 25. So first, the assignments. Chapter 25 centers on big data technologies based on the MapReduce and Hadoop. And we'll talk a bit about that here in a moment. Remember, this is a short week. All assignments must be completed by the date and time in Eastern Standard Time. So by the end of the last day of the class, make sure that you have that stuff in. There can be no exceptions to that rule. This week you'll be doing discussion 1, which centers on big data in chapter 25. It'll be worth 25 points due the last day of this week at midnight Eastern Time. Also, course project number 3 is due also at the last day of class at midnight. Um, the week 8 objectives, we'll be going over chapter 25, which talks about big data technologies. And they center on things like big data analytics and machine learning. This is a little bit of a data topic, but it'll be relevant for a lot. There's obviously courses where a lot more information of this that is shared. Hadoop and MapReduce is a little bit older, but it's still quite relevant, and it's certainly important to understand from a historical perspective. So we'll talk a bit about MapReduce, HDFS, which is Hadoop file system, Hadoop vTune, which is basically Yarn, and then also how MapReduce and Hadoop kind of works and how it is different in some ways similar to databases. Moving into the discussion for chapter 25. So how do you define big data? What are the implications for the 3 industry trends, the 3 V's, presented in the textbook, and what are the 3 V's presented in the textbooks, whether the 3 V's are volume, velocity, and variety. That's a pretty standard definition of big data. Talk a bit about what it means to you. Use your own words. Explain it in a way that somebody that doesn't use technology and know about technology might understand it. Looking ahead for the second discussion board, reflect about the course. What did you learn in this course? What are you looking forward to and looking ahead to so that you can learn more? So what are the things that have piqued your interest that you might want to learn more about? As you wrap up the course, your education into a successful career. So how can this stuff help you move forward? What did you learn? What was really compelling? And even what wasn't so compelling? So make sure that you share those items. Moving on to chapter 25, which centers again on big data technologies based on MapReduce and Hadoop. Jumping right in, there's basically been huge amounts of growth of data over the last few years, and a lot of this stuff has been fueled by, basically it started with Web 2.0, and then it went to another level at the point that social media took off. Also, sensors and the Internet of Things contribute a huge amount of data to this growth. So a lot of the information that's being exchanged today is actually being exchanged by system-to-system communications, not necessarily people. Also, lots of satellite imagery, communication networks, highly connected world. We now have ubiquitous computing and ubiquitous network connections pretty much everywhere. There are a few exceptions here and there, but as a general rule, most of the world is covered by some form of connectivity. We also have user-specific business data. That's all about personalization and capturing information that relates to me as an individual so that the companies can then tailor what I see, what I get based upon what I'm likely to buy in the case of retail, or perhaps what I need in the case of search. Big data basically refers to massive amounts of data. It's typically something that is also defined as something that can't be done using traditional approaches, such as storing it in a relational database. And it also is something that is related to big data analytics, which is using that data in some way to learn something useful. So what is big data? So generally speaking, we're talking about things that are in petabytes, exabytes, sometimes terabytes, but not so much anymore because terabytes is something that you can typically process with traditional systems. But it's not necessarily just the volume of data, which is what we're talking about when we talk about size, is how big is it? How many bytes does it take up? How large is it to store? Whenever we talk about big data, we also consider several other dimensions, which is velocity, which is how fast is it coming in? So In the case of streaming processing sort of situations, you may have something that is producing literally petabytes of data a day. So you could certainly not process that and you do something meaningful with that with traditional data processing approaches. That's where things like big data come into play. It's also the variety of data is a significant challenge. This is not just structured and relational data, which we're typically used to doing, but there's also semi-structured and unstructured data, which is data of varying degrees of structure, of ways of knowing what to get from where. To the furthest extreme of unstructured data is basically just text. It's data that has no structure, no meaning, no way of understanding what it's meant to be through some traditional approach. You might be able to figure it out based upon some parsing, but it's generally speaking something that is close to being natural language or just free-form text or images. So continuing, a V that doesn't necessarily always make the cut of the three Vs, but in my opinion, it definitely should be considered in the top four, is veracity, which basically means the credibility of the source. How trustworthy is it? And is it good for use? And the key concept with big data is that that data is of questionable quality or veracity. And so you basically have to use it with care. That means that typically whenever you're using big data, you're validating it rather than just trusting it. So whenever you look at something like a traditional data warehouse, you know that what's in that data warehouse is well groomed, well trusted. It is good as it can be. Basically, it is the gold standard within an organization. When you talk about big data, that's not the case any longer. The data that is stored may be very questionable. It may be downright noisy and could even be errant. So we approach it with a very different approach. Talking now about Hadoop and MapReduce. This is something that was really very revolutionary when it came along. The core components of Hadoop are basically MapReduce and the Hadoop file system. So the Hadoop distributed file system, HDFS. HDFS is what gave rise to what's now become known as a data lake. It gave the idea that maybe we should have really big storage systems that are distributed in nature. Hadoop started out as a search engine way back when, and the person that created it joined Yahoo, and then Yahoo decided to basically spin off Hadoop as its own company in 2011. It might have been different for Hadoop or for Yahoo if they had kept a hold of it. It could have been something quite useful. It has had tremendous growth and adoption, primarily because it solved a problem that in a way that was very elegant and very cost effective. By utilizing kind of commodity hardware and distributed processing in a easy to access sort of paradigm, it enabled people to write distributed algorithms that previously could not. And that's part of the thing that drove its adoption and why it became so popular. Moving on to MapReduce, that's kind of the thing I was just talking about. It is the way that we know how to do distributed processing. It's a combination of things, of basically an implementation in a runtime environment. But the idea is that you essentially write two things. You can think of them as functions. One of them is a map function and one of them is a reduce function. Not exactly what it is, but it's close enough, right? It gets across the idea that you're taking something and applying a map function across data, and then you do some stuff with it, and then you reduce the results of all that stuff into whatever it is that you're looking for. This allows for a relatively simple way of writing a highly parallel, highly distributed sort of solution that previously was very challenging to write. There were multiple attempts made at this early on with trying to take traditional programming approaches and doing things like inserting keywords that say paragraph or parallelism starts and parallelism ends and all kinds of stuff like that. But it really just didn't work out too well. What these guys did that was really clever was basically make it such that you essentially write two sort of functions or tasks that are executed in a controlled and known way, and it magically works. And that was what was really compelling. And it allowed developers to analyze really, really large data sets, again, running on commodity hardware. So not specialized computers, but hardware that was understood to potentially fail rather regularly. So the Hadoop system took care of that in an intelligent and robust way. And generally speaking, most things inside of the big data world are kind of structured around a key value pair. that especially MapReduce, it's all about key values. So the map function, as I talked a little bit about, is a generic function that takes a key of a value and it does some stuff with it and it returns back out of that uh, some additional key value pairs, right, with some key2 and v2. So it basically does some form of a transformation. The reduce is a generic function that takes those K2s and V2s and returns something of basically type K3 and V3. So it's doing additional transformation with the intent essentially to distill or to reduce. And so that's kind of the basic idea. There's more to it. We'll talk about it in a minute, but at the end of it all, that's really the secret. So here's kind of a visual representation of what occurs. And whenever you look at split 0, split 1, and split 2, that's one of the things that HDFS does for you is split files based upon kind of where they're at. And that was one of the key things that MapReduce did as well, was introduce the concept of doing the processing close to the data. So rather than having a data store that was external and you accessed it as an external drive or something, the processing occurred on the machine itself, next to itself. That was kind of the intent anyway. Didn't always work out, but that was kind of the intent. And the idea being, back whenever this came along, networks weren't quite as good as they were or are today. So keeping things local was kind of important. And that's where whenever you move from kind of the step of after you've done the map and you do a sort and then you move it over and do the merge and then the reduce, that step is the only kind of place where it's kind of going across the network, basically, is the idea. Doesn't always work out, but that was kind of the intent. Continuing the discussion on MapReduce, you can think of the word count solution is a very common description used in MapReduce, in part because it was a very challenging problem that was necessary to be solved at one point. It's pretty well solved at this point, but it's kind of the hello world of big data programs. So the idea is to basically the map function here is basically counting the instances of words in a particular thing and producing essentially a set of counts, and then you take those and merge those together. A more or more real example, this is that same kind of algorithm in the actual implementation. And so the map is essentially taking a list of text and words, and it's essentially splitting it and outputting the counts of those words. It's literally what it's doing. And then the reduce is taking essentially that list and kind of merging them together based upon their values. Other sort of implementations are things like distributed grep. Grep is a tool that allows you to apply a regular expression across files. Distributed grep is a way of doing that across a larger set of files. There's also the web link graph and these sort of algorithms. But one of the things that came out pretty quickly whenever we started talking about MapReduce was it wasn't ever really intended to do iteration, and that became a problem pretty quickly. Inverted index is another example. The idea is to come up with an inverted index of the document repository. So basically looking things up the other way around. A map function parses each document and emits some words, and then you reduce those to a document ID. So that's another example. And so on. So these are example jobs that have been done over the years. The Hadoop releases, the 1.x was a decent sort of offering. It had basically had HDFS and MapReduce. They incrementally done it, but the big thing came along whenever we did 2.0 and greater, so the 2.x releases. The main thing that they did was introduce a better way of resource scheduling using yet another resource navigator, so Yarn, and then some additional runtimes on top of Yarn, and also some improvements in HDFS that supported federation and increased availability. So incremental improvements. Hadoop file system, it is, as I mentioned, it's a way of accessing and storing large amounts of data in a distributed fashion. It's designed to run on a cluster, and it is intended to run on top of commodity hardware. This is commodity server hardware. It's not necessarily commodity retail or home user type hardware. So it is a little step up from what you might expect to run in a typical environment, but it's not something that is the supercomputer sort of scale of things. It's patterned after Unix. It's a sort of an implementation of the POSIX file system. It does do high throughput in a distributed fashion. So that and that's partly because of the way it spreads things out and how they're accessed. There is a name node that stores the metadata, and you store your application data on the data node servers, and you basically file content is replicated onto multiple data nodes, and there's a certain amount of name node replication that may go on as well. So with HDFS, the design assumption and goals was that hardware failures are the norm. Hardware is going to fail because it is commodity hardware. It was very much intended for batch processing. It's meant for large data sets and large files. And it has a very simple and not all that robust concurrency model, or coherency model as well. So one has to be a little cautious there. It is very much of a master slave or a manager worker sort of architecture. It decouples the metadata from the data operations. It replicates in a high reliability and availability model, and it attempts to minimize network traffic as much as possible, primarily because at the time it was created, networks weren't so good. There is a name node which maintains an image of the file system, and changes are basically write-ahead commit log in a journal. One of the things that you may encounter challenges is if you end up with a large number of small files, it will occasionally kill your name node server. So that's one of the things that will probably come up in our later discussions, which is the small file problem, which is namely uh, big data in general does not do well with a lot of tiny files. It does very well with a certain size file, and the exact size of that file depends upon the systems and the algorithms that are being used, but they're measured in it's typically megabytes, maybe larger, uh, not in kilobytes. So small files are not a good thing whenever you're doing big data. You also have a secondary name node, which serves basically as a checkpointing location and a backup node. It's going to have basically a copy of what's going on the main name node. Then you've got data nodes, which store the blocks in the node's native file system, so actually on the drive itself, and they basically periodically check in with the name node. The file system I/O, continuing that discussion, file I/O is around a single writer, multiple reader pattern. Files cannot be updated, only appended. So you don't go back and fix something, you typically add to, and that's a pattern that continues in most of big data. And in some situations, you can't even really append. Sometimes you can only create new, and the files become immutable. Um, the write pipeline is set up to minimize network uh, utilization. So the idea is to stay away from the network as much as possible. And the name node cluster typically spreads the things across different racks and then potentially across different switches as well. So it is aware of the idea here is to try to increase availability by not having things in one location, and the distribution is somewhere between racks and switches, and generally speaking, the algorithms get pretty intelligent about how far they keep those things apart. There is a replica management. The name node tracks the number of replicas and block location based upon block reports. So the idea is that what we're doing here is we're making sure that if something bad happens to a node, there is a copy of it somewhere else so that it can recover. Um, and then HDFS scalability. The example that's given here is that a Yahoo cluster achieved 14 petabytes with 4,000 nodes, 15,000 clients, and 600 million files. This is a bit dated. We've actually got much bigger than that. Moving on to the Hadoop ecosystem, once Hadoop came along, it was a really cool thing, and especially whenever you had Yarn, so you had a nice resource manager. Uh, Additional solutions were becoming available for Hadoop, things like Pig and Hive, which provide a higher level sort of way of talking to the data. Uh, Oozie, which is a way of scheduling and running workflows for jobs, and additional ways of essentially moving data from location to location. The list of these is continued to grow. HBase is another example. It's a column-oriented key value store that uses HDFS. There are many, many more now that over the years have been added. Those are kind of the top ones, but there are a lot of others. Some additional details on MapReduce. You do have a job tracker that keeps track of things, a task tracker that's also keeping track of the individual things that are going on. And there are some overall workflows that are going on, so that are kept and managed and maintained. The overall flow through the system is typically you submit a job, it starts up, it gets assigned somewhere, it gets executed, and then it finishes. Fault tolerance inside of MapReduce has several different types of failures that it can handle. A task can fail, and if it does, it essentially causes a runtime exception. Maybe the JVM crashes, whatever it might be. There's various reasons it might. Uh, and then typically those things get picked up. There could be a job tracker failure. It's not really recoverable in Hadoop 1, but I believe it is in 2. Shuffle is the idea where you basically are you get all the rows together is the idea for a given key. And this also has something to do with how you want to structure your data for um, consumption, and how you're partitioning it and how you're potentially, in the case of Hadoop, how you're spreading it across HDFS. The map phase, there's a background thread that buffers rows based upon the number of reducers in the job and the partitioners. You sort the rows by values. Then you have a comparer or a combiner that's likely going to be used. There's a copy phase and then your reduce phase. What you want to try to do with that shuffling is minimize the amount of shuffling that goes on to get the keys together, and that's something that is a potential pain and one of the optimizations that you spend a lot of time doing. When you talk about job scheduling, you want to keep track of the various work that's going on various nodes. It's a fair scheduler. Well, there's different types of scheduler. There's a fair scheduler and there's a capacity scheduler that's going to prioritize jobs based upon what the particular needs are. Fair scheduler is what the name kind of implies. Everybody gets their share. The capacity scheduler is going to potentially have a priority associated with various elements. Uh, Equijoins are a challenge inside of MapReduce. These are some various strategies that are used to address those, things like merge sort, map side, hash join, partition join, bucket joins, in-way join, in-way map side joins, and then simple in-way joins. Apache Pig kind of bridges the gap somewhat between being a database and big data, though make no mistakes, it is a big data solution. But it does allow you to write SQL. It's designed to solve problems around web logs, and that's one of the things in general. Most of these tools were intended to solve essentially log file problems. That's what this whole platform kind of came to be. We've since embraced it and extended it to do lots of other stuff, but originally that was the intent. It accommodates user-defined functions, so you can extend it to do things that it doesn't do natively. Apache Hive is kind of a higher level interface, again, using SQL-like queries. It supports processing of aggregated analytics queries, somewhat similar to what you might do with a data warehouse. It was developed at Facebook. Here's the basic idea of the Hive structure. There is a command line. You've got JDBC and ODBC going on for accessibility, and so on. So what are the advantages of Hadoop and MapReduce technology? So the disk rate is a limiting factor when dealing with very large data sets. So the idea is to spread that out across lots of different disks. Transfer speeds, an electronic feature, and increasingly steady. and then MapReduce processes large data sets in parallel. So this is all about distributing and processing in parallel, including things like writing to the disk. It handles semi-structured data very well and does very well with key value pairs as well. And it is essentially linear scalable, so that you can add more hardware and it just gets bigger and faster. It's not something that decreases as you add more, which some things do. You may have something that's essentially an exponential sort of growth where it starts tapering off, or a logarithmic growth. It starts tapering off as you get near the top. So reasons for developing with Hadoop version 2. In version 1, the job tracker became a bottleneck. The cluster utilization was less than desirable. There were different types of applications that didn't fit real well into the model, and it was difficult to keep up with the new open source versions of Hadoop. So version 2, and basically that's what you'd use today. I don't even know that anybody runs version 1. Quite useful. The Yarn architecture separates cluster resource management from job management, so it makes a distinction between the two. The resource manager and the node manager basically together can be used to form a platform for hosting pretty much any kind of application. And that's part of the reason why there's been such an adoption by Hadoop, the modern Hadoop, Hadoop 2.0, by most of the users in the open source world. That's pretty much all we need on that one. So some version semantics, schematics. Again, Hadoop 1.0 is interesting from a historical perspective, not really necessarily utilized any longer. So there are some other frameworks on Yarn. This is where I was talking about things that have additionally been added in. You've got Apache Tez, you've got Giraffe. It's essentially a graph processing environment. HBase, a very powerful environment. Whenever you consider Hadoop versus parallel relational database management systems, there was a time, and that's probably what this is looking at, that the advantage initially was to databases, and that's what this is saying here. Then it kind of shifted to a point where Hadoop sort of covered it up or caught up and actually exceeded. Now we're seeing that traditional databases have basically embraced a lot of the technologies, including things like eventual consistency and so on, so that they're able to now process data in a very a comparable approach and there's still a database. That's where things like Azure Synapse, Snowflake, and so on come to play. There is a general trend that you will see of exposing SQL to big data platforms, and that's what we're kind of seeing here. Part of the reason there is that SQL is one of the most common languages out there. So having things like HiveQL, it allows developers that might not have access to the environment to have access in a way that is unprecedented. There is a relationship between big data and cloud technology. I don't know that I would say that it's dependent upon, but there's definitely synergies there. The reason being, the cloud model allows for scaling up and scaling out in consumption-based pricing. So you pay for what you use, and you have access to resources that might be rather challenging to procure in a traditional on-premise data center. They also are highly automated so that you're able to extend things quickly with very little intervention by people. They're highly available, including geographically distributed as well. So I don't know that I would say that it's dependent, but there's definitely synergies. You can have big data without the cloud platform and a cloud technology, though you're probably going to be basically running your own kind of cloud at the end of the day. So yes, pretty hard to do one without the other, but you definitely can. You can do big data without cloud, and you could do cloud without big data, but they definitely go together very well. Some general discussions as well. The data locality challenges. The network can be a concern. It was much more so one in the past than it is today because networks have gotten really fast. You sometimes want things to become basically self-configurable and location-based data and virtual machine management frameworks in place. And so that you want your data close to you as a general rule. And that's going to be true pretty much of anything. If you're working inside of virtual machines of some sort, and at this point, especially if you're in the cloud, even if you're running a cluster, you're probably running it on a virtual machine. Very few things are going actually straight to the hardware these days. Most everything has a virtualization layer involved. Caching is always going to be useful in improving performance, be it data locality or otherwise. And it can be very challenging to optimize the depending upon your architecture to optimize resources across customers and so on. That's one of the reasons why big data has kind of shifted more towards a separation of compute and storage with things like Apache Spark and data lake platforms rather than a cluster-based approach such as Hadoop. Yarn has definitely been very popular in the past as a data service platform. Hadoop is becoming a data lake, and in fact, a lot of data lakes are actually replacing it. The cloud, and this is a situation where you do kind of have to go to the cloud. A lot of your cloud vendors are basically coming up with just a data lake minus the compute at a cost where you pay for just what you're storing, so you can access it independent of your cluster. That allows you to turn your clusters off. So that's one way of saving money potentially. SQL in Hadoop is getting better, but generally speaking, even if you're doing SQL on something like Apache Spark, you're probably better off learning the languages that are necessary to do it in a more efficient way. It might be good enough, but maybe not. Apache Storm is a distributed streaming engine. It allows for real-time data feeds, ties into this whole ecosystem. Oftentimes, things like Storm will be saving data to a data lake as they're coming in, especially if the data is of interest. So that's definitely relevant. There are always challenges in big data technologies. Data is inherently, whenever you start combining it across multiple data sources, going to be in conflict. And that's where you have this heterogeneity of information. You definitely have concerns around privacy and confidentiality. That means that most likely you need a secure data lake, not just a data lake. That means you need some form of security model on top of it first. And then you start storing your data in one location. You definitely have to have virtualization or visualization and better human interfaces. Tools have gotten very good at making it to where people can essentially do self-serve analytics on large amounts of data. And there's going to be inconsistent and incomplete information, as I've mentioned. The nature of big data is that your veracity is potentially quite low. That means that you're likely to have data that is at conflict with itself and perhaps even missing or incorrect. Whenever you're building solutions for Hadoop, there's likely going to be some variation of ETL, extract, transform, load, although lately it's moved more to an extract, load, and then transform, meaning you pull it from the source system, load it into the big data system, and then you do with it what you will that is necessary to do what you want to do. There's likely going to be some machine learning involved, probably going to be some graph processing. There's probably definitely going to be variations of different types of technologies. You will be dealing with lots of different languages as well. The programming models and metadata are not unified, and in fact, they're kind of diverging to where you need to know quite a few different languages whenever you're dealing with big data. The cluster is potentially quite large. A lot of the data fits into memory. That's where Spark really shines. Spark is an open source platform that does compute. That's what it does. It doesn't do storage. And originally it ran on top of Hadoop. Now it runs independently and can access pretty much any kind of data store. It is pretty much cloud only. So you can get it from Azure, AWS, or Google. And there's possibly a way of getting it on premise, but that's really rare. Databricks is a company that was created by the founders of Spark that basically provides a service for using Spark in a consumption-based way. it has a high degree of automation. We'll spin up clusters for you through clicks, shut them down, resize them as needed, and lots of good stuff. So definitely relevant to the conversation. So in summary, we've talked a bit about how big data technologies kind of are at the center of data analytics and machine learning. And that is very true. Machine learning at scale is essential these days. One of the things that you want to be able to do is to produce a machine learning implementation that can then be applied and utilized at scale and processing huge amounts of information. So that's one of the challenges we face today. MapReduce, very relevant in its day, less so today because it is actually shrinking in utilization. Part of that's because of cost. Having an expensive cluster running all the time, kind of a problem. We like to be able to turn things off, and we like to pay just for those cycles of the computer that we actually use. A Hadoop distributed file system, HDFS, still quite relevant. More so because of what it's enabling, which is data lake architectures. And generally speaking, HDFS like implementations, maybe not HDFS itself, but something very similar to it, is surfacing all over the place. Hadoop v2 and basically Hadoop using Yarn, that's pretty much a generic data platform that enables a lot of different solutions to run on it. Again, much less likely to be using it today than you have in the past, but it's still relevant. And we talked a little bit about how you might do MapReduce versus Hadoop, or MapReduce with Hadoop versus a traditional database or a distributed database system. And with that, I'll close with asking if you have any questions. Do let me know. That's what I'm here for. Stay safe, and I've enjoyed having you in the course. Best of luck with your future endeavors.